Hello and welcome to SETI Live. I am your host, Beth Johnson, Communication Specialist here at the SETI Institute. Unfortunately, Frank Marchese was unable to call in today, so I have taken his place. Sorry, Frank. Be safe. Have a good flight. Thank you to our viewers from around the world for joining us, and please let us know where you are watching from. Also, welcome into listeners on the podcast version of SETI Live, which is available on most podcast platforms. Thank you for listening. The fibered imager for a single telescope, or first instrument at the Subaru Telescope, is a game changer in telescope technology. Using techniques of aperture masking and spatial filtering, FIRST combines the power of spectro-interferometry to deliver high contrast capabilities and spatial resolution beyond the reach of traditional coronagraphic instruments. That was a lot of words, most of which I understand, some of which you probably did too. Joining us today to explain a lot of that is Sébastien Viviard, an exoplanet instrument specialist at the Subaru Telescope who has been working on this new instrument. Thank you for being here today, Sébastien, and welcome in.
Hi, Beth. Thank you for having me here today, and hi to everyone who's watching us from wherever you are.
So, Sébastien, start at the beginning. Tell us what the FIRST instrument is and its goal, what you're doing this for.
Yes. So you can pull up the first slide that we have. And so to start off, to kind of understand what the FIRST instrument is doing, I have to go back first to some basics and go back to high school physics that some of you might have seen, which is called the double slit experiment. The double slit experiment is about imaging a single star or light source with two holes or two slits. So if we look at the image that is on the left, we have the star sending light at infinite, and when the light goes through two slits and is imaged on a detector or a screen, you can see this pattern, this interferometric patterns, which is alternative of dark and bright fringes that is due to the wave property of light. And what you can notice is that the fringe spacing, the spacing between two bright fringes, is directly linked to the size of what's called the baseline, so the distance between the two holes, and lambda, which is the wavelength at which you're looking at. Now, if you consider the second image, right on the right, if the star is a little bit offset, has a little bit of offset, you can see that the fringe pattern that is created is basically the same, but shifted on the side. And when you look at two stars that are next to each other, those two patterns overlap, and you have differences of what's called the contrast, which is basically the difference between the dark and the bright fringe luminosity. And you have some phase. I won't go into those details, but basically this big pattern contains all the information that you need to know what are the positions, the relative positions between the two stars. So their distance or their position angle. And so what FIRST does is basically this, but with way more holes. What we do here at the Subaru Telescope, if we look at the image that's on the right, is we take the light that's coming from the telescope and we divide it using micro lenses. We sample the light of the telescope, and each of these sample of light is injected into what's called a single mode fiber. It's just a fiber like you have for the internet. And then we use those fiber to redirect the light and put them in the configuration that kind of looks like the double slit experiment, but here we have 9 slits. And then what we do is we create an image from all these holes, and we also disperse it using a prism to get colors information about what we're looking at. And that gives the image that you have on the bottom, which gives you basically 1 interferogram per spectral channel, so per color. And we use that to try to, the ultimate goal is to try to detect exoplanets, which are planets that are outside of the solar system and that are orbiting around their stars. Those are very compact objects, so it's very difficult to see. And we're also trying to analyze maybe giant stars that would have some convection cells on their surface, and also try to see protoplanets. So the idea is to see them, detect them, and then analyze the light that we get from them using the spectral information that we can have.
Okay, that was a lot to take in, and yes, definitely taking me back to my undergraduate physics classes. Okay, so how did this? Okay, before I ask this question, I'm going to welcome some people in, and then I'm going to let my brain sort of cycle through some things. Oh, Frank is actually watching. Welcome,
Hi,
Frank.
Frank.
Glad that you're there. Be safe through security. Okay, so we have people watching from Denmark, Majorca. We've got someone just from Europe in general. Boston, New Jersey. Frank obviously is watching from Dulles Airport. Maine, Italy. Delaware, Washington, originally from Oahu. Very nice. Welcome in. From Paris, bonjour. Mexico, let's see, more Denmark, more Paris. From Hawaii, welcome in. Aloha from the Big Island. Florida, someone in Dallas, Texas, Finland. Okay, so we got a very, very European audience today. That is fantastic. And now someone from Scotland, and also everywhere in the United States. So welcome in, everybody. Thank you again for being here. We are talking about a brand new instrument on the Subaru Telescope. So I know the goal of this is to detect exoplanets. That's one of the things that we have talked about. How is this different from classical imaging, from doing photometric analysis? How is this changing how you're going to look for and find exoplanets?
Yeah, so I guess I can start with what the challenge is to look at exoplanets. The challenge is that the exoplanets are very close to their host star, and they're very faint. So if you look at the star and the exoplanet, if you just look at it like this with a telescope, you cannot see the exoplanet because the star is so bright that you're basically blinded. And if you put the next slide number 2, there are techniques that have been used in the last few years that are very efficient. That is called coronagraphy. That is basically, simply put, you just put a mask in front of the star to mask the light coming from the star, and doing that, you unveil all the environment around this star. So here we have the example of an image of the HR8799 system taken at the Keck telescope. And so the star is behind this black mask that you can see, and we can see 3 exoplanets around this star. So that was a very nice discovery that was done. The only inconvenient, if I can say, of coronagraph is that you cannot see behind the mask, and it's limited to regions that are far outer of what your telescope can do. So if you do normal imaging, like a normal image of the telescope, you have a spatial resolution that is the smallest element that you can see with your telescope, that is directly linked with the wavelength at which you're watching and the diameter. So it's lambda over the diameter. And those coronagraphs can only allow you to look beyond 2 or 3 times the resolution of the telescope. So it works well, but we cannot see behind the mask. And what interferometry does, what we try to do with first, is to try to see behind the mask. And because the data analysis of the images that we get is completely different, we don't need a coronagraph. We just take images, and by analyzing those fringe patterns that I spoke about, we can retrieve spatial information of the object that we are looking at. So behind the mask, but even below the spatial resolution limit of the telescope, because we're not bounded to image formation when we use interferometry.
So can you sort of explain the basics of interferometry for me and for the audience? It's not a common term that we use in everyday parlance.
Yes. So when you do interferometry, when you do classic imaging, you just take one aperture and and you focus the light using a lens or something to create an image. But when you do interferometry, what you have, if you can put the first slide, you actually have two apertures that are interfering with each other. So those two apertures, you put a lens behind them, and you form an image that is the superimposition of the light coming from both holes. And what it does, because of light properties, it creates interferences, what's called this interference pattern, which is the alternation of black and white stripes, as we can see on this image. And so that's what interferometry is.
Okay, thank you. That's very helpful. So tell us about the design of this instrument. How did this go back? How long have you been working on this? How did it start?
Yes.
How did you end up now at Subaru?
So yeah, I'm talking on the behalf of all the first team and everyone who's been, involved in this instrument. There's been a lot of people. It's not just me. I've had a lot of help from other people than the first team here at Subaru as well. So I want to thank them for, giving me the opportunity to do this nice paper that we just published. But so the first prototype of FIRST was created in Paris Observatory. In the LESIA laboratory, and I think it goes back to 2007. And so back in the day, they made this prototype, and because it was working well, it was shipped to the US at the Lick Observatory that has a 3-meter telescope. If you can pull up slide number 3. And if everyone looks at the top row, the middle picture, this is a picture of FIRST that is installed on the Lick telescope, and we actually can see Frank on that picture with his white shirt, who's working with Elsa Huby, who's one of the co-PI of the instrument and who did work for her PhD on installing this instrument at the Lick Observatory. So because it was successful at the Lick Observatory, it was decided to put it on a bigger telescope, the Subaru Telescope, which is an 8-meter telescope. And so that's how in 2013, during my master's study, I got involved for an internship to come here in Hawaii and install FIRST on the Subaru Telescope with the help of Elsa and other people. So on the bottom picture where you see the Subaru Telescope, there's actually three of us that were in the first team originally. Guy Perrin, who's FIRST is kind of the brainchild. Elsa Huby, who was working with us and who basically taught me everything to align and use the instrument, and myself and 2 other students that were here as well, working on different projects. So if we look on the left, we have the first prototype of FIRST installed at the telescope where Elsa was helping me. Right above it, we can see how messy that looks inside. It's a lot of optics, it's a lot of cameras, fibers, very, very fragile fibers. And so I've been working in 2013 on that, and then came back to France, had my PhD, and then was fortunate to come back here in 2018 to continue trying to bring FIRST on sky and have nice data. So I've been working mainly on the hardware, making sure that it's aligned and everything. And so in the last few years, we were able to test the instrument on sky. So if we look at the right side of this slide, we can see actually it's me observing and using the instrument with the screens that are actually right behind me. And so what we do is we take these interferograms, so these images that are provided by the instrument, and with the help of others, I wrote an algorithm, or what we can call a data pipeline, that basically allows you to go from this raw image to you're looking at.
Okay. Sorry, you froze for a second there.
Oh, I froze. Oh, that's not going to
explain one more time how you go from the raw image to the graphing.
Yes. So from the raw image to the graphing, there is a whole data pipeline that I'm not going to go into, but it's basically analyzing the pattern of this image and try to find in these patterns all the information that you need to, for example, look at the relative position between two stars. And that's what we did on the Hokulei target to make sure that we were able to actually measure the position of the relative position of two stars. We used the instrument 2 times at 2 epochs to try to see if we could track the star orbiting around the other one along its orbit. And so if we look at the graph, we have Hokulei AA in the center, and we can see the orbit of the second star. And we observed it 2 times in 2020, and we were pretty close to get the theoretical position of the star. There are still some tweaks and things that we need to do to improve the accuracy of the measurements. But we're getting there, and that was a very nice result that we done. And the second thing that we've done was on the Keho'oea target, which is just a single star. And we use that to try to kind of assess the sensitivity of our instrument, which means how faint of a star or a planet or a companion we can see around another star. So what is their brightness ratio, and how close to the star we can go, because we know that with interferometry we can go very close to the star. And so what we found is that if we look at the graph on the bottom right, is that we can actually go pretty close to the star. This graph is the contrast of the companion that we can detect as a function of the separation from its host star. We can see in black dotted line the actual resolution limit of the telescope. So on the left side of this, you cannot do any image with classic image formation. But thanks to interferometry, we can go past this limit to the left. And we found that if we were to look for a companion around this star, we could detect something down to a quarter of the resolution of the telescope, and with a contrast of about 0.04 to 0.1, 0.15. So the contrast is not yet what needs to be for exoplanets, but we're getting there, and this is just a stepping stone for many other developments.
This is really kind of amazing. I thought adaptive optics was sort of like the most amazing thing I'd seen, but this is getting even more amazing to me. And I am not a telescope expert by any stretch of the imagination. I want to welcome in a few more people. We have people watching from Mexico, Kosovo, Oregon, and someone from Chile. So welcome in, everybody. And Finland. Hello, welcome in. So even more places. Thank you for joining us. We are talking about a new instrument that is being tested out on the Subaru Telescope. And so one of the things that you mentioned and actually was brought up in the chat, and I think is really important for us to touch on, is why you used the Hawaiian names of these stars. Why is that important in the work that you're doing?
So you can pull up the next slide. So I think that it's fair to say that when people think about the Mauna Kea observatories, from Mauna Kea, what they think first is that, and if we look at this picture, that's one of the best places in the world to do astronomy. That's what I did when I was a kid, and that's what brought me here today to work here. But I think that it's very important and necessary to acknowledge that this place is first and foremost a deeply sacred place for Hawaiian people and Hawaiian culture. And it is a privilege for me and for us, for everyone, to work here and even step foot on the Mauna. So my way of acknowledging this is to try to learn about the culture and to learn about the significance of star for the Hawaiian culture, and try to also communicate this information that I gather. So that's why when I was writing the paper, I really wanted to know more about these stars, their Hawaiian names, and I wanted to talk story with someone who has traditional knowledge about these stars. And I was most fortunate to find several people to talk with. And one of these people, who's Kumu Leilehua, we spoke a lot together, and she was kind enough to share with me some knowledge that she received when she was younger or throughout her life. And that's why I wanted to share this with everyone, and also discuss with her and other people how to properly communicate about it and how to integrate it in a science paper, which I think is important. And so what I gathered was that Hokulei, so the binary star that we looked, if you look at the literal translation, it means Hoku, stars, and Lei, that means garland. So some practitioner will say that it's translated as star garland, but there can be many meanings to this. And UN, for example, Leilehua, was taught the following translation. She was taught that it was a star constellation that rises like a cloud in the sky. So, in reference to the fact that Hokulei is the brightest of its constellation, and it's rising and guiding all the others in the sky. And so I think that it's very powerful to know these facts about these stars and not just have some numbers like, okay, this is this brightness in visible or infrared. And I think it adds more value to it. And when I looked up the second target, Keho'oea, I didn't find much information, and UN actually did not have many information about these stars. But in my research, the farthest I could look for information, I found that it was actually mentioned in the Kumulipo, and the mentioned name in the Kumulipo is Keho'oea in chant 14. And it says Leva Kihula Leva Keho'oea, which is, from my understanding, basically the creation of the stars in this Kumulipo, which is the creation chant in Hawaiian culture. And so I thought that it was important to share that with people in this scientific paper, because there's not a lot of written knowledge of this because Hawaiian culture was mostly communicated orally. So I think that it's a responsibility, and it's important to share this knowledge with the world, with scientists, with everyone, with people about the work that we're doing here. It has a very high significance.
I think that is an amazing sentiment, and I completely agree. And I appreciate that you took all of the time and went through all of the effort to research that. And I deeply appreciate that you have included it in this paper. So on a personal note, thank you. That is wonderful. We do have some questions from the audience that I would like to kind of talk about. And if anybody else has any questions about the research, the instrument, even some of the issues with having telescopes on a sacred mountain in Hawaii, feel free to ask those in chat, and we will try to get to some of them over the next few minutes. This question, I think, sort of applies to what the next steps are. So maybe you can explain where you're going with this instrument. Are there any sensors to convert optical information to digital electrical information for computer processing? So right now you're using fibers to bring the information in. What is the next step on this instrument that you guys are working on?
So the next step of the instrument, right now we spoke about the interferometry that is done kind of, we say, freely. So we have the holes, and we let the beams converge on the detector, and we look at the image. But there's also new technologies that are being developed for FIRST to increase its sensitivity, which is now to, instead of doing this slit experiment, which is to basically inject the light into very small, maybe like this, small devices. And those small devices have engraved fibers in them. Mm-hmm. And we do the recombination of all the holes onto this little device that's called a chip. And And so what we can do to answer that question, there are people who are also trying to have some different kinds of detectors at the output of this to try to analyze the signal. But what we're doing is we're keeping the optical sensor, the cameras, and the spectrograph and the prisms to disperse the light in order to get the information independently from the recombination of all the baselines. So the baselines is the combination of two holes, and because we have 9 holes, originally we had all the recombination done in one place, and with this new device, we're able to do the recombination independently for each of the pairs of holes. So that's what kind of the next step is in the research right now.
Okay, that makes sense. Catherine LaRue is asking kind of an interesting question here, and I know Frank would love this one. Is there any way to use sort of the developing AIs that are coming out to do quicker calculations or quicker hypothesis, better identification of exoplanets? Is there anything that can work on?
Catherine, hi Catherine. I know Catherine. She's my godmother. Um, that's a good question. From my understanding, ChatGPT is born from machine learning, and if the question is, can ChatGPT can it do that? I don't think that right now with the implementation of ChatGPT you can do that, but there are some developments in machine learning to analyze the images that we record, either with an interferometer, but also you mentioned adaptive optics. There's a lot of work that is being done with analyzing the images of adaptive optics system, interferometers, or any other kind of instruments that are brought on sky. There is machine learning that is being developed to try to increase the sensitivity and the efficiency of the instruments that we're using at the Subaru Telescope, but also in other telescopes in the world. So hopefully in the future, yes, machine learning, neural networks, and all these tools that are being developed will help a lot in analyzing our data.
Okay, yeah, there's definitely been a lot of advances. I mean, ChatGPT is its whole thing, but within the scientific community, machine learning has definitely become much more common. A lot. If you really want to work in big data science, learning how to code is the way to go. I have a lot of friends who are working on that, and I have to say that it is amazing what has been done. Even in my own research, from having to personally go through data point by data point and identify things, to now having an algorithm that can do it for me. That is a big change. So yeah, I do appreciate that we are looking at things like that. Giovanni has a fairly basic question, and I think it's important to answer and make sure we clarify. What is an exoplanet? And I know you explained it earlier, but some people may have joined later. What is an exoplanet? Is it something that is outside of the Milky Way?
That's a great question. So an exoplanet is a planet that is around another star. So when you look at the sky at night and you see all these stars in the sky, there is potentially, exoplanets, one or several, around these stars, just like our solar system, but somewhere else. So that applies to the whole Milky Way, so all the stars of the Milky Way, but also stars in other galaxies. So that's what an exoplanet is. It's a planet that is outside of our solar system, orbiting another star.
And they can be outside the Milky Way. It's just even harder to detect, because if you consider that the brightness of one star is hard to work with, and we're mastering that pretty well, but then you take a galaxy at a distance and it is a whole bunch of stars, and then it's hard to tease even the individual stars apart, let alone get even further in and tease out a planet. So yeah. But I do think it's important to understand, what we're hunting for all the time.
Yes.
And then there's one last question. I'm going to take this one. I know we're a little bit over, but I don't necessarily understand all of the words in this question, and I'm hoping that you will, but I'm going to ask it to you. Uh, is a large aperture phase mask, no lens, followed by an NNet reconstruction useful in this application?
So I think NNet means neural network. So we're kind of back to the machine learning questions. A
Mhm.
large aperture phase mask followed by a neural reconstruction. That's an interesting concept. I would need to put my brain a little more on it to kind of understand the setup and especially what the phase mask is doing to the phase of the light. But maybe I'm not going to say yes or no. I'm going to say that it's interesting and I would like to hear more about it.
Okay,
Uh,
so
but
Mike, you
yeah,
need to get in touch with Sebastian, and this could be a whole conversation. All right.
yeah,
Well, thank you, Sebastian. This has been wonderful, fascinating, interesting. I have learned a lot, certainly, and I hope our audience has too. Congratulations on getting first light for your instrument out at Subaru, and getting to
thank you.
look at some stars. That's pretty amazing. And thank you for being here today to talk to us all about it,
Thank you for
especially
having me.
joining us from Subaru with that wonderful wall of monitors behind you.
Yeah, well,
We
thank you for having
definitely.
me. And yeah, again, it's a teamwork. So it's not just me, it's a lot of people that have been working to bring this nice instrument on sky with these results.
And I know Frank really misses out being here because he's been working on this the whole time as
Yes,
well. So,
yes, been helping a lot.
um, yeah. So thank you for joining us. And as you get more results and you refine this instrument even more, we'd love to have you back to talk about it. Or
With
anyone
pleasure.
else from the team as well who wants to give it a shot. We would love to have any of you. So thank you very much for being here, and thank you everybody for watching. We definitely appreciate that you all come and join us almost every week. It's amazing. I see a lot of names that I recognize. So thank you for being here. As a final reminder, the SETI Institute is a 501c3 nonprofit, and we live on donations. That is how we do these outreach projects, like doing SETI Live, um, making sure that we're all here all the time, working on this, and bringing you the content that we think is interesting and surprising and fun sometimes. So, if you care to support us, please go to our website and click the Give Now button. And that helps our team continue to run these programs and make them better if we can. So thank you so much. And thank you to Sebastian. Thank you to our viewers. Thank you to Rebecca, who is in the background helping me run things. Hasmin is on vacation right now, so we're going slightly solo today. And Frank, get home safely, and we'll see you back here on SETI Live next week. So thank you again, everyone.
Thank you.